welcome to the deep dive. So we have a paper on the table today that tackles what might be, well, the single biggest problem in artificial intelligence right now. We talk a lot about the data these models need, all the books, the websites, the code, but the industry is hitting a wall.
A very real wall. We're running out of high-quality human text.
Which leads to the big question everyone's asking. Can an AI get smarter without us? Can it, evolve without seeing a single new word written by a human?
It's really the holy grail of the field. The concept is called self-evolution. And the paper we're looking at today claims to have made a major breakthrough. It's titled Agent0, Unleashing Self-Evolving Agents from Zero Data via Tool-Integrated Reasoning.
Zero data. That's the phrase that just jumps right off the page. But I want to be very clear for you listening. When they say zero data, they don't mean the model starts as a blank slate.
No, that's a key distinction. It means the training process involves zero new human input. Usually, to get an AI agent to perform tasks, you need humans to annotate thousands of examples. You write a math problem, then you write out the solution step by step.
Which is slow and expensive. And it also kind of limits the AI to what we already know how to do.
It creates a ceiling. If it only learns from our examples, how can it ever really surpass us?
People have tried to get around this, right, with things like self-play.
Right, and self-play works wonders for closed systems like chess or Go. But for the kind of complex, open-ended reasoning we want from language models, it often just fails.
That's the stagnation problem.
It is. The model just ends up recycling its own knowledge, its own biases. It creates this little echo chamber where it might sound more confident, but it's not actually getting any smarter.
Okay, so how does Agent break that ceiling? If there's no human teacher and it can't just talk to itself, where's the new insight coming from?
The innovation here is really a combination of two things. First, they split the AI into two separate entities. You can think of them as a teacher and a student.
A teacher and a student, okay.
And second, and this is absolutely crucial, they give the student a tool.
A tool.
A code interpreter, a sandboxed Python environment.
So it's not just thinking in language, it's actually executing code.
It brings objective reality into the loop. The paper calls the architecture a symbiotic competition. They take a standard base model, in this case Qwen 3 base, and they initialize two agents from it. One is the curriculum agent.
The teacher.
And the other is the executor agent, the student. But here's the twist. The curriculum agent isn't just trying to help the student pass. It's trained to propose what they call frontier tasks.
I'm looking at the reward structure here, and it's fascinating. The teacher is actually rewarded for finding the very edge of the student's ability.
It's actively searching for that Goldilocks zone. They measure this by looking at the executor's self-consistency. The curriculum agent gets its maximum reward when it finds tasks where the student's consistency score is around 0.5.
So not too easy, not too hard.
Right. If the student gets it right 100% of the time, the teacher gets no reward. If the student fails 100% of the time, also no reward.
It forces the curriculum to stay right at that perfect tipping point where learning actually happens. But where does the tool, the code interpreter, fit into this?
That's the second part of the reward signal. It's a tool use reward. The researchers knew that if you just let two language models talk, they tend to get stuck in simple chat. So they explicitly reward the curriculum agent for creating tasks that require the executor to use the code interpreter.
So it can't just ask, what's the capital of France? It has to ask something like, calculate the sum of the first 50 prime numbers.
That's the idea. It forces the executor to stop just recalling facts and start actually reasoning and computing. And this creates a virtuous cycle as the executor gets better with the tool.
The curriculum agent has to come up with even harder problems to keep that difficulty level at 0.5.
A self-reinforcing spiral of improvement. The better the student gets with the hammer, the harder the nails become.
I want to push on that teacher idea a bit more. How does it stop itself from just asking the same few hard questions over and over?
That's a real risk. They call it mode collapse. To stop it, they added a repetition penalty. They use a metric, a BLEU score, to compare new tasks to others in the batch. If the teacher starts repeating itself, it gets penalized.
So the tasks have to be difficult, they have to require Python, and they have to be new.
That's the whole objective function. And they optimize this curriculum agent using GRPO, which is a method that avoids needing a whole separate critic model.
Okay, let's switch to the student, the executor agent. This is the one actually doing the work. What happens when it gets one of these frontier tasks?
It's a multi-turn process. It's not just a single answer. The executor will read the problem and start reasoning in text. It might say something like, okay, I need to figure out this pattern, but the numbers are too large to do in my head. Then it triggers a tool call. It literally writes a block of Python code.
And the system just runs it.
It runs it in the sandbox, and the executor sees the output. Now, that output could be the right answer, or it could be an error.
A syntax error or divide by zero.
And that's the reality check. A language model can hallucinate a fact and convince itself it's right. But code, well, code either runs or it doesn't.
It gets immediate objective feedback. It can self-correct.
It mimics a human debugging process. It sees the error, thinks about why it happened, adjusts the logic, and tries again.
But since there are no humans here, who's grading the final exam? If the executor says the answer is 42, how does the system know that's correct?
This is the hardest part of any zero-data learning system. They use a method called pseudo-labeling, specifically majority voting.
A sort of democracy for algorithms.
In a way, for each task, they have the executor generate, say, different responses. If the majority of those responses arrive at the same answer, that answer is treated as the correct one.
That sounds risky. What if the majority is wrong? What if the whole class decides 2 plus 2 is 5?
That's the label noise problem, and it's a huge deal, especially on those hard frontier tasks the system is designed to create. A standard training algorithm would just see that correct label from the majority vote and reinforce the error.
It would just double down on the mistake.
And there's another problem with standard reinforcement learning. It uses something called clipping to keep the model stable.
Which I assume stops it from trying out wild new ideas.
It does. It discourages the model from trying low probability tokens. But for really hard problems, the correct reasoning path might be hiding in those low probability options.
So to fix this, they had to develop a whole new algorithm.
A new algorithm just for the executor. They call it ADPO, Ambiguity Dynamic Policy Optimization.
ADPO. So how does that handle the wrong majority problem?
It has a component called ambiguity-aware advantage scaling. It basically scales the learning update based on confidence.
So if there was a lot of disagreement in the voting,
If the consistency was low, the update is made smaller. It learns more cautiously when it's confused, so it doesn't overfit to a potentially wrong answer.
it refuses to just blindly trust a shaky consensus. What about the other problem, the exploration?
That's handled by the second part of ADPO, ambiguity-modulated trust regions.
Trust regions.
You can think of the normal clipping mechanism as a leash. You keep it short to keep the model from running off.
Okay.
ADPO makes that leash dynamic. For ambiguous, difficult tasks, it loosens the leash.
It lets the model explore more on the hard problems.
It gives it more room to stumble upon a new, correct way of reasoning that it would otherwise have been prevented from even trying.
So we have this symbiotic competition, the tool integration, and this clever ADPO algorithm. Let's get to the results. Does it actually work?
The numbers are pretty substantial. They
Yeah.
tested this on the Quen 3.8b base model. After the self-training process, its mathematical reasoning performance shot up by 18%.
18% is a massive jump for a base model that saw 0 human-curated math problems during this phase.
And what's maybe even more interesting, its general reasoning on benchmarks like MMLU Pro improved by 24%.
Wait, it got better at general reasoning than at math, even though the system was pushing it to use Python.
It seems to be a real transfer of capability. By learning how to break down complex math problems into logical, codable steps, it just became a more structured thinker overall.
How does this compare to just, giving the base model a calculator?
They did that comparison. The base model with tool access improves a little, but Agent0 significantly outperforms it.
So just having the tool isn't enough.
No, the agent has to learn the strategy of how and when to use it and how to interpret the results.
And what about against other self-learning methods?
It outperformed them. It beat methods like R0 and absolute zero. It even outperformed Socratic zero.
And Socratic 0 uses external OpenAI APIs, doesn't it?
It does. So Agent0, working completely in its own little loop, did better than a system that could call on a much larger external model for help.
I want to look at the case study in the paper, where they show how the questions evolve.
Mm-hmm.
What did that look like?
At the beginning, in iteration 1, the curriculum agent was generating pretty basic geometry problems. Calculate the area of this triangle.
Standard textbook stuff.
By iteration 3, it was generating these complex constraint satisfaction tasks. The example they give is about designing a parade route where adjacent neighborhoods can't share any digits in their addresses.
That's a huge leap in complexity. That's logic, planning, optimization.
And the executor solved it with a hybrid approach. It used natural language to understand the spatial constraints, and then used Python to verify the numerical solution. It was thinking like an engineer.
Conceptualize in language, verify with code.
Exactly.
They also did ablation studies, right?
Yep.
To see which parts mattered most. What happens if you take the teacher out of the equation?
If you don't train the curriculum agent, so the teacher never gets any better, appearance drops by 9.3%. The teacher has to learn along with the student.
And without the reward for using Python.
A 7.2% drop. If you don't explicitly force the tool integration, that virtuous cycle just never gets started. The tasks don't get complex enough to drive real intelligence.
And what about the new algorithm, ADPO versus the standard GRPO?
Using ADPO prevented a 1.9% drop. That might not sound huge, but in model tuning, nearly 2% is a very significant gain. It proves you have to handle that ambiguity intelligently.
This whole framework, it paints a picture of a self-sustaining intelligence loop. The AI is effectively writing its own textbook.
It is. It's deciding what's worth learning next.
It completely removes the human bottleneck. We used to be the limiting factor because we couldn't create and annotate data fast enough.
And now the AI writes the problem, solves the problem, grades the solution, and then writes a harder problem. It's a paradigm shift from imitation to exploration.
Which brings us to a final thought. If the AI is designing a curriculum based on the edge of its own ability, that edge is a moving target.
And eventually, that edge might move beyond our ability to fully understand or audit the problems.
We wouldn't be able to check its homework anymore.
We would have to trust the process, trust the output of the code.
And that's the reality of Agent0. It's a glimpse into a future where machines could become their own and perhaps best teachers. That wraps up this deep dive. We will see you on the next one.